Dear students, welcome back once again to the Econometric Methods course. In today's module, we are going to discuss about the problem of multicollinearity. In the last few classes, we had been discussing about the problem of autocorrelation and heteroscedasticity. The problem of multicollinearity is very similar to the problems of the things we discussed earlier. This issue is very important in the regression models. In today's module, we are going to discuss about the meaning of multicollinearity and the consequences of it and the sources of multicollinearity problem. Let us continue our discussion on the meaning of multicollinearity. Now let us define the multicollinearity issue. This term multicollinearity was first coined by Ragnar Frisch. The problem is very specific to multiple linear regression model. We already know there is a OLS assumption that no high or significant correlation among independent variables. Multicollinearity problem is specific to multiple linear regression model. We already know that there is a OLS assumption that no high or significant correlation among the independent variables. Multicollinearity is a situation of high degree of correlation among two or more explanatory or independent variables in a multiple linear regression model. Consider the following MLRM. YI is equal to beta 0 plus beta 1 x1i plus beta 2 x2i plus ui. Multicollinearity is said to be perfect when x2i is equal to alpha 1 x1i or x2i is equal to alpha 0 plus x1i or x2i is equal to alpha 0 plus alpha 1 x1i. So, this is the perfect multicollinearity. This may be written as small x2i or the deviation from mean measures x2i, and this one x1i is the deviation from mean measures. If the multicollinearity is perfect, small x2i is equal to k times x1i. The degree of multicollinearity will vary. Different degrees of multicollinearity may be defined as the correlation between x1 and x2 is between 0 and 1. So, in the case of complete multicollinearity, x2i is k times x1i, otherwise the correlation will be between 0 and 1. That will be depicted differently. Now, let us see the consequences of the multicollinearity problem. Consider a multiple linear regression model in its deviation form. Small yi is equal to beta 1 x1i plus beta 2 x2i plus ui. We already know that in this equation, beta 1 hat is equal to sigma x2 y sigma x1 square minus sigma x1 y into sigma x1 x2 divided by sigma x1 square sigma x2 square minus sigma x1 x2 the whole square. Variance of beta 1 hat is equal to sigma hat square into sigma x2 square divided by sigma x1 square sigma x2 square minus sigma x1 x2 the whole square. So, this is the formula we have already seen. When the multicollinearity is perfect, let us see what happens. When the multicollinearity is perfect, that means x2 is equal to k times x1. If you substitute this in the original equation, we get the original estimator, we get k times x1 for x2 y, sigma x1 square minus sigma x1 y, sigma x1 k times x1 divided by, here inside here in the denominator you substitute for x2, we are substituting k times x1, and then we are just squaring and rearranging the terms. So, we get k times sigma x1 y, sigma x1 square minus k times sigma x1 y, sigma x1 square divided by k square. This is a square, so we can take outside, then the terms are the same, so the whole square you can put. So, k square times sigma x1 square the whole square minus, here also you can take this k outside, that is k square, inside you have 2 x1s multiplied. So, x1 square the whole square the outside. So, if you look at this equation, both these terms are 0, right, the denominator and numerators are 0 because the terms are the same. So, subtracting them is 0. So, you get 0 and 0 both actually in the numerator and denominator. This means beta 1 does not have value, beta 1 is indeterminate. This happens when the multicollinearity is perfect. So, in the presence of multicollinearity, you will not be able to estimate the regression coefficient. Now, let us see what happens to the variance of beta 1 hat. That is equal to, we are just substituting x2 as k x1. So, substituting this value we get in the previous estimator for beta 1 hat, we get sigma hat square sigma k x1 the whole square divided by sigma x1 square sigma k times x1 square minus sigma x1 k x1 the whole square. So, just again substituting this value for k x1 and rearranging the terms, we get sigma hat square k square sigma x1 square divided by k square sigma x1 square the whole square minus k square sigma x1 square the whole square. So, the denominator terms are the same, and so subtracting it would give you 0. So, you get in the numerator you have got the positive value and the denominator you have got the 0. So, the value of it is infinitive. So, when the multicollinearity is perfect, the variance of beta 1 hat is infinity. So, it has got implications. So, this holds true for other regression coefficients as well. In this case, the beta 2 hat will also have the same kind of problem if the collinearity is perfect. Let us take the second case when the multicollinearity is significant though not perfect. That means let us define the multicollinearity, the correlation between x1 and 2 as R12. We already know the formula for the correlation coefficient. Correlation coefficient R12 square is equal to sigma x1 x2 the whole square divided by sigma x1 square into sigma x2 square. We are going to now substitute, actually we can use this equation and we may substitute R1 square into sigma x1 square sigma x2 square for this term sigma x1 x2 the whole square in the estimator of the variance of beta 1 hat. If you substitute in the equation, you get sigma hat square sigma x2 square. In the denominator you get the change of terms sigma x1 square sigma x2 square minus R12 square sigma x1 square sigma x2 square from this formula. So, now we can rearrange and we can cross the terms in the numerator and denominator. We get sigma hat square sigma x2 square, and this can be cancelled you get to know only these two terms, and that can be written as sigma hat square divided by sigma x1 square into 1 by 1 minus r2 square. So, this is the variance of beta 1 hat, and we may write the standard error as well for this. That is, standard error of beta 1 hat is equal to sigma hat divided by sigma x1 square into 1 minus r2 square, the square root. So, now we may infer from this that standard error of beta 1 hat is proportional to the r1 2 hat r1 2 square. That means, when the correlation increases, the correlation between x1 and x2 increases, the standard error of beta 1 hat is inflated by some factor. So, that is what it says. Let us denote the problem or restate the problem as like this: variance of beta 1 hat is equal to sigma square divided by sigma x 1 square into 1 by 1 minus r 1 2 square. This term is taken as the variance inflation factor. Actually, this is the factor in which the standard error is the variance is inflated. So, we may define this term as variance inflation factor of the first regression coefficient. For the extended multinomial regression model, multiple linear regression model, this can be extended like this: variance of beta I hat is equal to sigma hat square divided by sigma xi square into 1 by 1 minus ri square. That is the multiple regression coefficient. This is the multiple correlation coefficient, and this is derived from this auxiliary regression equation. X1i as a function regressed on x2i, x3i and xki. If there are no k independent variables, then this auxiliary regression would give you the multiple correlation coefficient. So, from this multiple correlation coefficient, we may define the variance inflation factor. So, variance inflation factor is nothing but 1 by 1 minus ri square. Actually, this ri square is derived from the auxiliary regression of x1i on the rest of the independent variables. So, this is the generalized version of the result we derived. Variance of beta I hat is equal to sigma hat square sigma xi square into vi f I. So, naturally, the standard error of bi hat is equal to sigma divided by sigma xi square square root of sigma xi square into square root of v I f I. So, we can say the standard error of beta I is in proportion to the square root of v I f. As the v I f is higher, the standard error will be inflated that many times. We already know v I f is indirectly proportional to the multicollinearity or the correlation between the independent variables, and so the standard errors of the individual regression coefficients are inflated with the rising multicollinearity. So, that is the first result we can derive. So, the multicollinearity is directly affecting the standard errors of the respective individual regression coefficients. When that gets affected, the value derived, that ratio derived, the t ratio is also gets affected. The t values are deflated or rendered insignificant with increasing or higher multicollinearity. So, that is the second result we can derive. That is the second consequence we can derive from directly from the above. The T ratios are deflated or rendered insignificant with increasing higher multicollinearity. Then we can say the next result we can derive from this is multicollinearity widens the confidence intervals, because the confidence intervals are defined like this: beta I hat plus or minus 1.96 the square root of VIF I standard error of beta hat. Of course, this is derived at the for the 5% level of significance. So, this confidence intervals are also inflated by the factor of V square root of the VIF. So, that is also widened. So, the confidence intervals derived in the presence of multicollinearity will give you the inefficient confidence interval. Another important problem is high sensitivity of the error estimators for the specification. So, it is highly sensitive, because for instance, addition or deletion of independent variables will change the signs and magnitudes of the regression coefficients which are affected by the multicollinearity problem severely. So, when you add new independent variable or delete independent variables that are affected by the multicollinearity, the signs and magnitudes will greatly vary. So, that is another implication or the consequence of the multicollinearity problem. In the presence of multicollinearity, the estimates of the regression coefficients are not involved in this problem would not be changed much. So, that is another consequence. Actually, if the multicollinearity problem only affects the regression coefficients of the independent variables which are affected by the multicollinearity problem, otherwise it will not affect the other independent variables that are not affected by the multicollinearity problem. At the same time, the goodness of fit measures like R square, R bar square and F would not get affected by the presence of multicollinearity. So, that is the result. It will be very interesting to see. Now, let us see the sources of multicollinearity problem. There are several sources of multicollinearity problem. The first one is the data collection method employed. For example, limited sampling range determined by the values of dependent variables due to a selected population would be a prime reason for the multicollinearity problem. The second reason could be structural constraints on the model. For example, a regression of electricity consumption on income, household size. There is a conceptual constraint that families with higher incomes generally have larger homes than families with lower incomes. So, naturally, in this model, the income and household size will be related. So, this would cause the multicollinearity problem. Thirdly, the functional specification of the model itself. For example, adding polynomial terms to a regression model, especially when the range of x is very small, will lead to the multicollinearity problem, because the polynomial terms will be linearly related. The fourth reason for the multicollinearity problem could be the overdetermination of the model. This happens when the model has more explanatory variables than the number of observations, or relatively the more number of variables in relation to the sample size. This could happen in medical research where there may be a small number of patients about whom the information is collected on large number of variables. The additional reason for multicollinearity, especially in the time series data, may be that the independent variables included in the model share a common trend, that is, they all increase or decrease together over time. Thus, the regression of consumption, expenditure on income, wealth and population the regressors' income, wealth and population may all be growing over time at more or less the same rate, leading to a multicollinearity problem among these variables. So, these are all the problems, common problems that causes the multicollinearity in a regression model. So, with this we will conclude this module. We have so far seen the meaning of multicollinearity and the consequences of the multicollinearity problem, and we saw the sources of multicollinearity problem. In the next module, we would see the different tests available to identify the multicollinearity problem and the possible remedies for the multicollinearity problem. So, with this we will conclude. Thank you. Thank you for attending this program.